So lesson 8, any questions from the homework? Went okay? So today we are going to finish off the unit. Well, we sort of did last day. Today is mostly a putting everything together, looking at weird curveball kind of questions review lesson. What I want to try and do today is clear up or help you keep straight what's what. My biggest concern on the test, I'll ask kids to find, for example, the electric potential. That's the voltage. And kids will find the potential energy. And Connor, I got to give them 0. I can't even give them any part marks because technically, normally I give you like part marks for writing down the right formula. I haven't even done that. And then I really can't give any marks for being able to plug in numbers into the wrong formula. It'd be like if I asked you to find the force and for some reason you found the momentum. I can't give you any part marks. I gotta give you 0, even though they're both in the same unit here for electricity. So read along with me. Some hints. This might be one of the pages that you want to look at when you're studying. First of all, example 1. You want to make sure you convert charges correctly into coulombs. The most common charge we've been using is this little micro symbol. What is that little micro? What is 1 microcoulomb the same as? Please, anyone? 10 to the negative 6. Let's write that down. Coulombs. Also remember that we have the charge on 1 proton and 1 electron. So we have a proton charge and come here. Proton charge and an electron charge. What's the charge on a proton and an electron? Well, you need to know that an electron is negative. Sorry, but we expect you to have some science background. You need to know that a proton is positive. What is the charge on an electron or a proton? The symbol we use is E for elementary charge on your formula sheet, but this is one worth having in your head, I think. 1.6 times 10 to the negative 19 coulombs. Okay. Then it says, example 2, solving for the correct quantity. Fill in the correct variables and the units in the column 1 below. What variable do we use for force? What letter on our formula sheet is force? This is meant to be really obvious, Brianna, yeah? F. Units. What letter do we use for electric field? Not F. Okay, capital E. Units, there's 2 of them, and you can figure out the units by looking at your formula sheet, because here's an E. What would these units be? What over what? Look at the quantities. Okay, newtons per coulomb. Also, here's an electric field right here. What over what? What is V measured? Volts per meter. Okay. Really wasn't worth a high five. It was a V over a D, please. PE. Now I use PE. First of all, what does PE stand for? Potential energy. On your formula sheet, they don't use PE. On the formula sheet, they use E with a little p like that. I will always handwrite PE because you'll notice, otherwise I'm worried I'll get this E confused with the other E. I wish they would just use a capital P, a capital E. I understand why. They don't want to use 2 letters as a variable. Fair enough. They like to do subscripts instead. Oh, what's potential energy measured in? Help me out. Okay, that's always been. Another handy one, maybe, just to help you remember. If I rewrote this, what would potential energy be measured in? Think about the units if I got the potential energy by itself. Turns out, volt coulombs. I've never used that, but that might help you remember that energy is also voltage times what's QV. voltage. Now, part of the problem here is we have another word for voltage, which I hate. The other word for voltage is potential. Listen, please. On your test, on a written question, I'm going to ask you to find the potential at a location. 1/3 of you are going to find the potential energy and get a 0. I haven't found a way yet, aside from repeated warnings, to try and beat that out of you. Please understand the difference between potential and potential energy. Potential energy, voltage. Potential energy is the one of those. Symbol, letter, V, and I always put the wings on it. Now the units are volts, but what was a volt defined as? Well, you can figure out what a volt was defined as by looking at the units from here. Here's where we defined voltage. This is energy. What do I measure energy in, Jacob? What do I measure Q in, charge in? We defined voltage as how many joules per coulomb at that location. The very last one is work, symbol W. Okay. Then it says, use the correct point charge parallel plates formulas. Fill in the formulas in columns 3 and 4, rows 1 to 4. So let's go. Can I fit? No, I got to shrink down a little bit. First of all, how do we find the direction for a force? It is a vector. Let's make a little note here. Vectors. These ones are scalars. For forces, how do we figure out which way the force was? Well, here we used like charges what? Repel. Opposites attract. Okay. How did we find the force between 2 point charges? This is where we started out this unit. We called this Coulomb's law. We said if you want to find the force between point charges, it's going to be K Q1 Q2 over R squared. If I want to find the force that one charge exerts on another charge, like that. What if I want to find the force that a charge is experiencing if it's between parallel plates? Well, there we walked off, instead of using the point charge force equation, we used this. Oh, but we had to get the F by itself. Connor, get the F by itself. We said this. F equals QE. Oh, but we also then said, oh, and by the way, if you're between parallel plates, what's the electric field between parallel plates? Not that, because that's for point charges. What was the electric field between parallel plates? This bad boy. Oh, wrong one. Look, we really said this. What if my points weren't all nice and lined up on the same plane, on the same level, in a straight line? What if we had stuff at angles? Well, what we did here is we add tip to tail, and we used the principle of superposition. Connor, we said, look, if you give me 3 charges, I can't. There is no equation for 3 charges. What I'll do is I'll ignore one of the charges, find the forces between the first 2. Then I'll ignore the first charge, find the forces between the second and third one, and add them together tip to tail. What about electric field? Okay, for electric field, how did we find the direction? We asked a question. What question did we ask? Which way would a positive want to move if it could? The short way of writing that is this: from positive to negative. The only reason I don't like the short way is sometimes your diagram doesn't have a positive or it doesn't have a negative in it, and you're but I can always figure it out by saying, well, which way would a positive want to move if it could? Because there's always one of those two in the diagram, sometimes not both. How do I find electric field? Well, the variable was E. Oh, for a point charge, right there. KQ over R squared. Can you make it, Emily? Because you're looking bad. You're like this. The mouth was half open. Stay focused. Doing a half job of studying and a half job of learning, they both won't work. You got to commit to one. Oh. How do I find electric field between parallel plates? Doink. Now, there's the definition of electric field as well, but that allowed us to get change in voltage over distance. What if the electric fields weren't in a nice straight line or in different directions? Again, we add tip to tail. Okay. Now, for potential energy, voltage, and work, am I going to be trying to figure out the direction? No, they're scalars. But what that means is this. For all of these, we include the positive and the negative signs. We don't include positives and negatives here. In fact, if you recall, when I gave you the equations, each time I mentioned some textbooks put absolute values around the charges because we decide the direction. But for the scalars, you put plus and minus signs in. Emily, the easy way to remember that, for forces and fields, for this row, no signs. For scalars, put the signs in, negatives and positives. You can't have negative work. You can't have negative energy. That's going to be really important because if you don't, you may be supposed to, maybe if I'm asking you to find the total energy of the location, maybe you were supposed to go positive plus negative and get a smaller answer. And if you don't put the negative in there, you get a bigger answer. Right? Potential energy between point charges was K, Q1, Q2 over R. What was the potential energy between plates? Oh, this one. Except get the potential energy by itself. What if stuff wasn't lined up? Who cares? It's a scalar. Just add them. No tip to tail. Just add them. Combine. Add them up. What's the total energy? Add up the energy from the first one, energy of the second one, total energy, add them up. Well, Brandon, what about voltage? Doink. Ah. That's voltage. That's got voltage. Oh, which one of these do you think is the voltage from a point charge? The ones that have the R's. Yeah. Voltage equals KQ over R. Again, you include... Oh, hang on. That's going to go over here. Sorry, guys. Again, here you include the positive and the negative. You can't have a negative voltage. That's just fine. That just means that positive charges would want to fall there. Negative charges would want to move away from there. What's the voltage between parallel plates? Oh, you can either think about it that way, or you can think about it that way. This was our definition of voltage. We defined it as energy per coulomb. I probably write it here, though. It's going to be voltage is ED, where E is F over Q. You know what? Is F over Q times the distance between them. Well, yes and no. Really, what I should have written is this, Connor. They tell us. Think about all the parallel plate diagrams that I gave you, Jacob. Didn't they always just tell you the voltage from the battery that was hooked up to? Yeah. That's why I've never had to bother showing you that one. But they'll tell you. Now, if it's from point charges and they're not lined up and I say find the voltage right there, do you need to add them tip to tail? No, no. They're scalars. Just add them. Work. For work, we also include... Oh, don't use green again, Mr. Dueck. Change colors. We also include the plus and the minus signs. Now, for all of these, we'll almost always be going work equals change in potential plus change in kinetic. But here, for point charges, change in potential is going to be K Q1 Q2 over R final minus, I need more room, Mr. Dueck, here, change in potential is going to be K Q1 Q2 over R final minus K Q1 Q2 over R initial. Between parallel plates, change in potential is going to be Q change in voltage. That's kind of a rough summary of everything we've done for the past couple of weeks, Mitch. Let's try applying some of this. It says correctly find vector direction for force and field. Don't assign a direction for positive energy or voltage, but include the positive and negative signs for, did I say positive energy, potential energy, and voltage, but not for forces and fields. Forces, fields, forget the signs. signs for scalars. Whatever dumb way you want to remember it. Or you can remember it, Brianna, hey, the first row, no signs. And technically this is electric field, so not that either. These ones, but the signs. So to solve problems correctly, make sure that you calculate the point charge work using energy and not using force, because force is changing. It says fill in the final row on the previous page, we already did. Why can't we use force times distance? Force is not constant between point charges. Why can we, between parallel plates, why can we use force times distance or change in energy? Well, the force is constant between parallel plates, but I'll be honest, I almost always just fell back on change in energy because it was QV, which was quick anyways. Force times distance, Q times V, you're still multiplying two things together, so I use that most of the time. Jacob, is he going to make it? I don't know. Okay. Step 6 says add vectors to find the total force and field. Add scalars to find the potential energy and voltage. Fill in column 5. We already did. Let's do a question. Once again, Joel, this is kind of a glitchy old diagram typo. This is supposed to be microcoulombs and microcoulombs. This was typed in Word 95 for Mac, and the diagrams are slowly degenerating over the years. Okay. If I give you two charges like this, what can I ask you? Except replace the word can with will. What will I ask you? Well, one of the first things that I can ask you to find the force, magnitude, and direction on the positive charge, on one of the charges. Find what, Zay? Part A. Force. F equals, is it between point charges? K, Q1, Q2 over R squared. Where K is what? Q1, am I going to put a negative in here? Brianna? Why? It's vector, we take care of the direction. So 1.5 times 10 to the negative 6 microcoulombs, there we go. 4.2 times 10 to the negative 6 microcoulombs. Divided by, what's R? Careful. Sorry? No, it's not 36. Careful. 0.36, right? Find the magnitude of the force, please. You get 0.3, you get 0.4375? Yeah? 0.438 newtons, because 3 sig figs. Direction. So it asked me to find the force on the positive charge. This positive charge, is it being pulled to the left or pushed to the right based on this negative charge? Brianna? Pulled to the left, why? Unlike charges attract, okay. Left. So that might be something I could ask you on your test, give you 2-point charges and say find the net force. Or I could say find the voltage at a location between them. I'm going to call this charge 1. I'm going to call this charge 2. To find the voltage, well, you'll notice, Matt, in my point charge voltage equation, there is only one charge at a time. That tells me I'm going to find the voltage from the first charge, the voltage from the second charge, and to find the total voltage, since they're scalars, Matt, do I need to go tip to tail? Nah, add them up. Okay. My strategy is going to be find the voltage from charge 1, which is K Q1 over R1. 9 times 10 to the 9th. Trevor, am I going to put a negative in this time? Yeah. Negative 1.5 times 10 to the negative 6 divided by, and R1 is 0.12. The left-hand charge is sending out a voltage, and at location, the little dot right there, the voltage from the left-hand charge is negative 112,500, and I'll carry all the sig figs, Connor, because it's not my final answer. The right-hand charge is also sending out a voltage. It's going to be 9 times 10 to the 9th, positive 4.2 times 10 to the negative 6 divided by 0.24. Get rid of the negative. 4.2 divided by 0.24. The right-hand charge is sending out a voltage, and at that location, its voltage is 157,500. So, total voltage is going to be negative 112,500 plus 157,500. And Trevor, can you see if we hadn't put the negative in here, we'd get an answer in the 200,000s, which is way too big, instead of what the actual answer is, which is the net voltage right there, 45,000 volts. Keep doing a lowercase v for voltage. It's an uppercase V for voltage. Okay. Connor, is that 2 or 3 sig figs? Then we're good. C. The work required to put that big a charge there. How much work, if we started out at infinity and we moved a positive charge right to there, how much work would we have to do? Well, work equals change in potential plus change in kinetic. Point charges, so I definitely can't use force times distance. Let's, I think, argue that starting and stopping at rest. Okay. By the way, what would the voltage be out at infinity? What would make sense based on how we've been defining things? If volts is how much energy you have per coulomb, and out at infinity we said you have no energy, how many volts would you have out at infinity? Also 0. Okay. Now, look up. Change in potential. What did I just find in part B? Voltage. You know what? Although I could go potential energy between the final, you know what? I think a quicker way is going to be to recognize that I can go Q, V. Where little q, Kayla, is the charge that I'm moving. How big is the charge that I'm moving? Oh, it says 4.75 times 10 to the negative 8. And I know what the voltage, I guess I should have written the change in. I know what the change in voltage is because my initial is out at 0 and my final is 45,000. You know what my change in voltage is? It's 45,000. This gives us a nice little shortcut. Instead of us having to do a bunch of potential energies and then add them together and then go change in potential, I got the voltage. I already did most of the work. It's going to be this times 4.75 times 10 to the negative 8. How much work? Let's see, 2.14 times 10 to the negative 3 joules. That's how much work. What would be doing the work? Some outside source of energy, little invisible angels or something. Turn the page. Is that okay, Brianna? Yeah? We talked last day about the cathode ray tube, how a television worked. So below is a side view of a cathode ray tube and a front view of the screen. So you need to imagine that you are sitting right there observing the TV. Yes? Am I wrong? Yo. It actually works for both. It's a, you know why? Look up. We defined voltage as energy per charge. See, this is the definition of electric field, which means it actually works anywhere. This is the definition of voltage, which means it works anywhere as well. The definition of voltage was energy per charge, which means energy is also charge times change in voltage. Okay, I know I put it underneath the electric field, underneath the parallel plates one. It's because this is actually, these two are the definitions. They work anywhere. We define electric field as newtons per coulomb. Did I answer your question okay? Yeah? Okay, back to here. Turn the page now. So here's us looking at a TV screen. We have our negatively charged plate right there. This would be positively charged, so it'll yank electrons from the negative plate, and we would have this hooked up to a plug, so there's an unlimited source of electrons, and they, boom, come shooting out. Okay? We have two sets of plates. We have two plates like this, and then we have two plates that are aligned vertically. These ones can deflect it left or right. These ones can deflect it up or down. So here's the question. It says, A, where will the electron dot end up? Right now, initially it's hitting dead center. Choose from A, B, C, D, E on the diagram. If we make the upper deflecting plate positive, if I make that positive, will this electron, which is normally hitting dead center, hit in location A, B, C, D, or E? Think about it. Well, don't write this down because I'm going to muck up this diagram. If this is positive, which way will this electron get tugged as it goes through here? Up. So what would that appear when if I was peering into the screen like that? Location what? Sorry? You're right. Louder? Hey. Right? Yeah? Mitch, yes? Make sense? Yeah? Okay. Location A. Oh, what if instead, okay, we turn these plates off. What if instead we make this right plate here positive? So visualize the electron coming through. It's not going to get deflected here at all. Boom, it gets deflected here. Which way? What would it look like over there? Caitlin. Caitlin. B, yeah? I can't tell if you guys are totally lost, drooling like Connor, or just right? A positive, it would yank it towards that right-hand plate, so facing straight on, you would see it get deflected to the right. Location B. What if we made both the right plate and the upper plate positive? Where would it get deflected to? E. Okay. This is how you can put an electron. Is that okay, Brett? How, what, okay, which one? This is you sitting, that's why we drew the little person right there when you were still back on the previous page. You're staring this way. So right now you see this, okay? If they charge this right-hand plate positive, the electron would get pulled towards the right-hand plate as it went through here. It would get yanked to the right. We would see it hitting there. Yeah? This last one, if we charged this positive, and it would get yanked up as it came through here, and yanked to the right, it would get yanked up and to the right, it would get yanked to location E. Okay? Try a little bit more. Next, we adjust the voltage so that the electron is hitting right there due to the upper plate having a positive deflecting voltage. Where will the electron dot end up? Choose from A, B, C, D, all those letters. If we, A, increase the deflecting voltage. So what if I bump up the voltage right here? How will that move this dot? I heard it. G. It's going to get deflected even more. Okay, go back to here. 2, what if I reverse the polarity and make the bottom positive and the top negative? Where will it get deflected to? I heard it there. See? Right? Okay, go back to the original again. What if I increase the accelerating voltage, not the deflecting voltage, not these voltages? What if I bump this voltage up so it's traveling faster? If it's traveling faster, do you think it's going to get deflected more or deflected less? Ah. So what do you think? A. Is that okay? Yeah? Okay. It says explain your answer using principles of physics. We just did. I'm not going to ask you to do one of those using principles of physics. But this is the technology that allowed us to put an electron anywhere we wanted to on initially a circular screen back in the 1920s. And then the electron would hit, it would cause some paint to fluoresce, and on the other side you would see a dot. Do that a bunch of times and you can make a picture. So, example 9 says this. In what way does our simple model of a cathode ray tube explain how black and white television works? Only one dot or pixel is hit at a time. By sweeping the Y voltage, this one, from positive to negative, we can move the beam up and down on the screen. We can step the beam over left and right using a small X voltage and then sweep the beam up and down again. So all you would do is you would start out right here, sweep it up and down, move it over a tiny bit, sweep it up and down, move it over a tiny bit, sweep it up and down, move it over a tiny bit, sweep it up, put a bunch of dots, move it over a tiny bit. You would just keep doing that. It goes faster than your eyes can detect, but it also explains why the old black and white TVs could give you a headache after a while from watching it, because it was just barely faster than your eyes could detect. So we gradually put more and more dots, more and more dots. If we gradually add increments of X voltage, then sweep vertically, we illuminate the entire screen. The TV signal turns the cathode ray tube beam on and off as it sweeps the screen. The beam on is a white dot. The beam off is a black dot. The beam partially on with a lower is a gray dot. In this manner, a picture is created. TV. Surprisingly simple technology. Except not flat screen TV. Okay. What's your homework? Number 2. Four. 7, 8, 9. Okay, and then here's the big one. Test is going to be on Tuesday, April 17th. Okay.